Well, greetings, Webby people. Today we will be continuing to work in Engo. This is part 3. We will be building that Frogger game that we started 2 videos ago. So here's the game as we left it last week. So here's the game as it is. Currently it's not a game really. You can't move the frog around. The cars are just growing out from the middle, creating a new one every second. Each one has a vector it keeps going in by a movement system, which we created. So that's what I want to do. Now what I want to do is I want to get the cars coming from the sides instead. So they come from the side, go to the other side, and then when they reach the other side, they disappear. Because we don't want to just keep having thousands and thousands of new cars coming, constantly slowing down the system. The other thing we need to happen is I want to get the frog working. So to do that, I need another system which will handle controls. So we'll get those two working hopefully today, and let's get coding. Yeah. Where are we? So over here, tab edit, play. What have we got? Frog.go. We're working on the cars first, aren't we? So we need spawn system. We play spawn.go, because our spawn system is currently creating the cars, but very lazily I've put the cars at a random place in the middle. So instead of doing that, I'm going to get a random integer first. So hang on. So we're going to create a new car. Maybe we'll make more than one a second. Maybe we'll create one 0.2. So we'll have 5 cars a second from various different places. We'll see. If they're going not fast, that should be okay. Row colon equals rand dot int n. I think we get to give it a parameter, and we'll just say 7. Direction. We'll create a velocity component now. So vel colon equals engo dot point. So we're making a point to define where he moves, and this is just his velocity, not his position. None of the cars are going to move in the y direction, so we'll just set them all to 0 there, and we'll put the x as 7. Oh no, this makes sense. 7 modulus 2 times 2 minus 1. So 0 times 2 minus 1 is minus 1, and 1 times 2 minus 1 is 1. So we end up with minus 1 and 1 as our velocities. Although actually, maybe we should make those velocities slightly higher. So times 20. I'm not handling the keyboard very well today, sorry about this. Minus 10. So that will set a velocity to either 10 forwards or 10 backwards. Obviously we need to decide where we put the car based on that. So that's pos colon equals another engo dot point. This time the row will be based on the number, so it would be its y will be 7 times. How big are our cars? I guess spawn is the one that's making the cars. Yeah, here we're making cars. Common dot rectangle. So width is 100, height is 50. So we just put times 50, and that's not 7, that's row. and it's and that was a mistake here. Obviously, where I put 7 here, this needs to be row mod 2, and its X position is either this is slightly trickier, but you can kind of get the same effect. It's row mod 2, and so we've either got 0 or 1. So if we times it by 700 and take away 100, then we can get our, then we'll either get minus 100 or 600. So, slightly odd way of thinking. I tend to do my creating stuff where I need to switch on pairs using that system. I could understand why people wouldn't want to. So now when we create our new car, its position is no longer that, it's pos. So let's find how far this goes. That's all that point there. So we get rid of that and put pos. Oh, undo that. Oh, pos, and its width is 100, height is 50. We'll leave that. Color rectangle, velocity component. That's a thing. That's a component that we created, but basically just stores velocity. And engo.point. That's right. So we just put vel in here. Ci vel. And in theory, we should now be creating cars. Do more or less the right thing. There are bugs already. Spawn.go cannot use row mod 2 times 20 as type int as type float 32. Of course you can't. So let's just convert that to a float. Float 32. Nor it can use float 32 around here, and the same here. Is that all of my errors? Yeah, so now our cars are starting over there, or they're starting over there and going that way. So that's a fairly nice bug. Times minus 700 plus 100. So we've either got, yeah, that should do the job. No. Oh yeah, it's times minus 700 plus 800. There's always a way of getting from to any two numbers to another two numbers with a times and an add. So that's going that way. We've got the other ones coming yet? We might need to increase their speed as well. There they are. They are coming. I think this needs to be the 8 and this needs to be the 7. And let's make them go a bit faster, because I wasn't enjoying watching those cars come really slowly like that. There we go, so we got cars coming. But our frog isn't doing anything, and the cars will keep coming forever. And there are way too many of them. A gap. That's actually a gap between several cars. Like, so if we increase the speed of the cars again, R to 60 and that to 30, and we might find that one is enough. Whatever. And we'll get fewer cars, and there will be more gaps, and the cars will be coming faster. And are any of the gaps going to be big enough to drive through? Yeah, plausibly. Okay, so we have cars coming. There's a couple of tricks you can do to work out to put the cars on at different times and to make sure they don't crash. I'm not going to worry about that. I just wanted to have some cars. The next thing we're going to do is we're going to make sure that we kill the cars when they get off the map. So let's create our killer system. Spawn. Let's tab edit play destroyer.go. So package play, and we are making a new system. So type bounds destroyer, and that's a struct. And this one basically needs a list of all of the cars, doesn't it? What does it need? So because everything we need to work this is actually going to be the same things as a movement object, we need to know which direction it's moving, we need to know how fast, we need to know where it's going. So I'm just going to use a movable. So we'll have its obs is a slice of movable. Is it movable? Well, we got cars. Cars are movable. Movement entity. But the add by interface method takes a move eable. So there's an E in there. I think that's all I need. Type func BD, which is a pointer to a bound system. Bound system, and that is update, and of course that takes a D, which is change in time, float 32, and the other function we need, bound system, and that is remove, which takes an ECS dot basic entity, and func BS pointer to bound system add, and I'm just going to add by interface lazily. I see no major benefits. You can argue with me on this one if you like. If you get used to using ECS, they want you to store. They tend to store them in their own brand new kind of struct. I'm actually feeling like just storing the interface and handling it as an interface, which has its advantages and disadvantages, as I'm sure you'll see. I prefer interfaces. I think Golang is all about interfaces as a language. If you get to using interfaces more, but then when you're using someone else's library where they tend to work in struct, you kind of want to think, well, okay, let's try and work somewhere in the middle. So, add by interface. We need to take a movable, and obs. Oh, it's bs.obs equals append bs.obs. Oh, so that's the add method. Easy as pie. The update method. Oh, when we create this, we also need something which has to be set by someone else, and that is, we need the world. Is that right? Yeah. I think that needs to be a pointer, actually, just in case there's some confusion. And our update function will look at each car. So for I comma c colon equals range bs.obs. That's OBS is just objects. It's probably not the. And for everything in here, we just need to go through. If it should die, tell the world to kill it. So, I'm actually briefly going to copy the struct t colon equals bs.obs. Remember, it's just a struct slice, so my motive for doing this is so that this doesn't get interrupted when the destruction happens on in the remove. So we'll range over t. Because when we call the remove function, it's going to pull it out using weird slicing stuff. So if c dot get space component dot position dot x is less than, tell you what, x colon equals all of this. If x plus so if sc dot x plus w plus sc dot w I dth is less than 0, then we need to kill it if it's going in that direction, right? vc colon equals c dot get velocity component. Again, these are both methods that belong to the movable type, so velocity component position. Nope. I got a little bit confused there. This needs to be dot position dot x. And width is less than 0. And vs dot vel. We've got it stored as vel. Vel dot x is less than 0. Then we need to kill it. So the kill method will be w.remove, and then it's c.get basic entity. So you end up having to do it through brackets here, which I can see, if you put it in its own struct, then that gets rid of that problem. But and we need to dereference that. Can you dereference it in a single go? Because that will return a pointer. What I'd like to do is just put that and just follow the pointer. Although I think I had a problem doing that in the past, so that may throw a wobbly, and if it does, we need an extra line of code. If sc.position.x is greater than, what was that number? 600, I think, the width of our program. Greater than 600, and vs.vel.x is greater than 0. And then it's the same. Seem to have created a whole other thing there. That feels right for number of bits. Let's get our removal method working. Let's go copy that paste from the removers tab, edit, play, removers.go. Okay. And this is remove. I was vaguely tempted, and I probably will do this. This definitely feels like something where you can generate code, because every bit of this needs to be exactly the same. So I will probably switch this to go generate by the time I've written about 10 of these. Not just yet, though. So, remove movable. This now takes an array of movable and returns an array of movable. And we go through the list. Movables have that ID method. Do you know what? They have the method, but movables don't. So, well, it's probably faces. Tab edit. Play faces. Okay. Why not just add that method I want here? ID u int 64. Because that's still guaranteed to be completed by anything that meets, and the movable naturally handles that too. So now when I do the removers, we get the ID automatically, and this is type automatic, so I think that works. So now we go to destroyer.go. Faces. Gonna yank that, and I'll put that in here. And it's bs.obs. Okay. And that, again, I really feel like this should be an interface. The remove thing, and it should the interface should just be ID, so that anything that has a get ID method can be, or has an ID method that returns to uint64, can be received. That way you can just send a struct around and no one cares. So carry on. So that removement thing is now in existence. So Quick tick. This just calls the remove movement. No, movable. Let's just be movable. Movable. So, every system has an update, a remove, and most of them have an add because you kind of need to put stuff into them. But this currently doesn't do anything until we get to... Where's our scene dot go? Let's get rid of that. Tab edit, play, scene dot go. In here we create our sys list. And now we need a... What did we call it? Destroy sys? Bound system. Bound sys. Colon equals... No, colon. And this is an and bound system. And this needs W. Oh, like that. Close with a comma. But that doesn't exist. Syslist doesn't contain that. Did I put that in faces? Spawn, maybe. Here it is. This now needs a death system. Yeah. No, bounds we call that. Common dot. Nope, no, it's just a... So, that's now part of that. And in the scene we create one. And here, w.add system. Systems dot bound sys. But we haven't yet added our frog to that. Oh, that's because the spawn. No, it's the car. I keep saying. When we create the car, we need to add it to the right system. So ss.systems.boundsys.add by interface. So now we've added the car to. So now we've added the car to the bounds death system. We should find that it all works. You never know. So let's give it a go. Let's see what the problems are. Undefined W in w.remove. So that's in Destroyer 20. I think that might be because it was a capital W. And of course it's not bit W, it's bs.w. And this again is bs.w. Try that again. Remove. It's not called remove. What is it called? Okay, so it's not called remove. It's called remove entity. It's called remove in each individual scene, but this will remove it from all. So what remove entity does is it loops through all of the scenes in the world and calls remove using this entity. So there might still be a complaint, but we'll see. Undefined E and E.id. Destroy.go 30. 30. There we go. So, fairly standard mistake there. Forget to actually give your type parameter a name. And 16, I declared and not used. Yeah, I wonder why I thought I was going to use I. Never mind. So now we have the cars created. Check now is to see whether they get destroyed when they reach the other end, which is about 600. So we'll wait a second and see if they do. Cars are coming along. Our frog still cannot move. So we're hopeful that when the cars reach the point where the other ones are created, they begin to disappear. They do indeed. There we go. I'm pretty happy with that. We have cars we can avoid. It's not a very pretty Frogger game, is it? But that's fine. Also, we should make there 9 rows. Let's do that. 9 rows. That shouldn't take too long. Scene. Nope. Spawn. Spawn system. R9. That's better. 9 rows. Okay. So. Next challenge. Move in that frog. Well, we need a control system, don't we? What do we have already? I'm going to create a new file. Play control.go. And this obviously fits in the same package as usual. And we need controllable. So this will be a component, although I think we had a components page, so I might go to that. Tab edit, play components.go. Type control component struct. Most important thing in this, we need key commands. Type, type key command. So what we're going to do is we are going to create a type called a key command, so that our frog can tell us what keys it wants to listen for. And then when we create our frog, we will tell engo which keys it wants to use. So a key command contains it needs a key name. I'm just going to call that K, and that's an engo.key. It needs a word that's going to be a string, so that's how it will be passed through the system. So S, and that's string. And the last thing we need is an action that's going to happen on that. And because how I'm just going to move this frog around is I'm just going to, at least for this version for now, the quick way is I'm going to give it a point. So we'll call that point, and that's an engo.point. Okay. And most of this actually feels like it's going to go in control.go. I think I'm organizing it badly. So I'm going to put this out, put that all in here. So a control component needs an array of key command. It's not quite right, is it? Okay. Commands. Okay, so we're happy with that. We've got a slice of key commands, and the key commands are going to be how we actually make these things. This allows me to do 2 frogs, because I quite like the idea of having 2 frogs. So I'm going to write a function that does that, a func get controls, and this will take an n for the player num, and that's an int, and it will return a control component. Later on, if you're making something else, I'm actually quite tempted by the idea of using this, of having a function that operates on something here as the key as the component instead of a key. But I'll let you play with that idea later. If n equals 0, return control component. That doesn't even need to be a pointer, does it? Because you can pass that as a slice without too much trouble. Yeah, I'm just going to not bother making that a pointer, and that commands colon I feel like this ought to work. So we have an engo.key, so engo.arrow left, and that associates to L1. That's left for player 1, and then our point will be left is minus 50, comma. Oh, this does need to be engo.point. You need to clarify that. Engo.point minus 50 naught. Any complaints? Missing comma before new line. A couple of them. And we should be able to do 4 of those. Right, up, down. And these obviously aren't quite right. Right is 50. This is 0, minus 50. And this is 0, 50. And outside the brackets, let's just copy all of this again. So I'm only going to create 2 sets of controls here. Controls for player 0 and controls for player 2. For player 1. And this is now A, S, W, and D. Right, that makes sense, doesn't it? So, standard other keys that we use for those things, and I should probably replace all of these ones with a 2. I wonder... No. So here we go. So we have 2 sets of controls that we can get. So when we create our frog, we can give it this. And a control component also. If we give this a method, we'll create 2 methods for this. One, func get control component, which might be helpful for some interfaces. Struct. No, that's a method. And it belongs to control component, doesn't it? CC pointer control component. Get control component. And this returns... Oh. And this returns a pointer to a control component. And then return CC. And the other thing I want to do is just have a func called get controls, because that's actually more useful. Func get controls. No. and this is get controls, and this returns a slice of key command. That is slightly easier to handle, and this returns cc.commands. Because of course that method will be inherited directly by everything that contains a control component anonymously. So that gives us a lot of strength for manipulating it. And we'll do that when we create our frog. So let's go back to our frog creation. New frog, n pnum int. Okay, so we now take a parameter for the player num, because when we create this we need to give it a control component. Control component and so our control component, and that is get I can actually get away with that, I think. Maybe I make it new controls so that it's clear it's a constructor. Frog.go. Yeah. So this is now new controls, and we just take pnum. So now our frog contains a control component, which now means it implements the method that's needed for our control system. Control.go. So now we're going to create this control system, which I might have already created the... No, I haven't. Good. So now we need the control system. Control system. Struct. Yes, I know. I forgot the word type. Type. Control system struct. And as usual, this will have obs, which is a slice of... And on this occasion... controllable. I'm just going to go to faces and create a controllable type, so I can work with type controllable interface, and a controllable is a basic face. Obviously we need that. We need a space face and a control face. And where did we define? So engo velocity face, my basic, and the last set is combi. So here we'll have a type control face, and that's an interface. The most important part of this is actually get controls. Which returns a key command. But I will include in this get control component, just for some level of internal consistency. Control component. So we have space face, so we can move it around. We have a basic face, so we can point to it, and we have a control face. So back to removable, movable. No, not that one. So it's got an array of constructors. So our update type func cs pointer to control system, and we'll have an add method. I'm going to add by interface just to be consistent with the names. And this takes C, which is controllable. We're going to have a func pointer to control system. So we have a couple of those. And this one we need is update, which takes D, which is a float 32. And this one, which is remove, which takes a E, which is an ECS dot basic. What? Oh, entity. So now our basic. I'll write the remove function later. We may not actually need it, but we have to have it there to be the interface. So add by interface. OBS. Oh, cs.obs.add. cs.obs.add. Nope. Equals cs.obs equals append cs.obs with C. Easy peasy. The control system dot update for C colon equals underscore comma C colon equals control range So now what we're going to do is we're going to go through all of the object in this system. If we've got one player, then there will only be one object, but if we have 2 or 3 players, then there's 2 or 3 objects. So just going to stick it in a for loop in case we can do that. And then so for underscore comma C colon equals range cs dot obs. So we're working through that range. And then we look at every single key they have. So for underscore comma kc, that's a key command, colon equals range cs dot get, no, not C, it's C dot get controls. And as we loop through that, we check engo dot input dot button. This is an if. So it's a package singleton really, but it keeps track of all of the button keys, and we ask specifically if it's got the S button kc.s equals dot just pressed. There are a couple of options here. Just pressed means just put down. There is pressed, or which if it's still pressed, if it's been pressed many times. But this will only be true the first time update happens after the press. So you only get one response to this, which is kind of handy. And in this case, C dot push. I really want to have a couple of extra functions attached to space components and do more with interfaces so that I can do it lazily. But sc colon equals c dot space dot get space component and then so now we do sc dot position plus dot add engo, oh no, and then it's kc dot p, which that should work. The only problem is we're not actually listening for the keys yet. You need to tell engo to listen to the keys. So when we create the frog, we're going to go through in our scene. Oops. We need to add them to the system. So the syslist. No, the spawn doesn't need to know about these, so don't need to worry too much here. But w spawn sys, we do need a control sys colon equals and control system. Now that didn't need anything, but we do need to add it. Control sys dot add by interface fg, and to tell engo to listen again, we're going to need to do engo dot register inputs or something. Hang on, let me just quickly check. So here we need engo dot input dot register button, and then you need the name of the button and the key, which might be engo dot. So that would be kind of what it looks like, but obviously we're going to do this in a loop using our frog's controls. So for underscore comma kc colon equals range frog dot get controls and so now we work with kc dot s, and here kc dot k. So here we have the key. So this will tell engo that we need to know about these keys, and so it will create messages and store the things that need to be stored when the keys are pressed, and attach it to the string, which is the name we gave to it, either L1 or L1 or whatever. And have we added the system to the systems? Nope. So w.add system, and that's control sys. So in theory we should be able to move our frog around now. Key command redeclared. Control.go. Control.go. Oh, did I try and declare it somewhere else? Previous declaration. Frog. Did I never save? Let's WA. Yeah. So 30. Missing type in composite literal. Control 30. I think that solves that one, and obviously I'll need to do that here as well. 59. Undefined engo. Why do I always do that? Not enough arguments in call to new frog. Of course. Frog. So we changed our frog to take a player num. I'm going to use the arrow pad. Can set it to player 0. So we have a frog. And our frog moves. There's a clearly 50-step jumps. It's listening to the keys. I'm not going to bother making them slower for this one. I came up with a system that was quite nice and softer movement, but I'm just demonstrating some of the capabilities here, so I'm not going to worry about that right now. Whoa, and our frog is going around, but there are no collisions. So next week, hopefully we will be able to handle collisions. I'm going to leave it here today. Hopefully this will have helped you understand some of how we can do engo. Don't forget to like and subscribe if you haven't already. Hit the bell if you like, and maybe get notifications every time I put something out. Yeah, so next week is all about collisions and the message system. Till then, goodbye.